You're welcome to yet another of our series of lectures in inorganic chemistry. This lecture will be running in all areas of inorganic chemistry. But for today, we want to start our discussion dwelling on the D block metals. If you take a look at the periodic table, you'll agree with me that the table is subdivided into four major components. The component that has the S1 and the S2, and the component that lies as a valley just after S2. Thereafter, you get to the component that rises to almost the same level as the S component to the opposite end, called the P block element. Directly under, even though our table here is not showing the F, is the F block. The S block are mostly metals. The P block are supposed to be non-metals, but due to transition in electronegativity, they show some tendency of metallic property as you have metalloids belonging to the P block. But our interests for today lie particularly on the valley that exists between group 2 and 3. This is that valley that contains the set of elements we call the D block elements. The D block elements lie between groups 2 and 3, as you can see on the periodic table displayed here. Here you have members of group 2 who are the S2 elements. Just after the S2, you have the D falling into the groove you see here, and is bordered on the right, on my right. I wouldn't know how you are watching the video. On my right, by the P element. Our vested interests in the transition element arises from their peculiar properties, peculiar character. This has informed why scientists, engineers, College of Medicine, and all agriculturists, technologists, the electrical, and all forms of persons study members of this group due to their versatility. As we have said already, the D block elements are all metals. They are all metals. The D block elements are all metals. And how do we say they are metals? We say they are metals because they show the properties of metals. All the members of the D block family are solid in nature, except mercury. They are opaque. They are good conductors of heat and electricity. They are sonorous. They are also ductile. They can be torn out into wire. They have reasonably high density. They are lustrous. Due to the electron cloud in the metal bond. They have high tensile strength, and they are also malleable. As we had stated earlier, the D block metals are divided into two major classes. the non-transition d block metals, and the transition d block metals. The non-transition d block metals within the family are characterized by the possession of completely filled d orbitals, as shown in the schematics in the next slide. And they comprise of all the members of the d block except scandium, copper, zinc, cadmium, and mercury. These elements mentioned are d block elements, but they on their own have some other that qualify them to be called another name. To prove this, the IUPAC schematic shown here shows you that the d block metals, which are non-transition in nature, have completely filled d valence orbital. The n-1 n quantum state minus 1 d orbital of a non-transition metal d block element must have completely filled d orbitals. You can see from our orbital diagram, here you see the rising energy. Here you see the rising energy. The s orbital at the least, the p the next higher, and the d the highest, made up of 5 suborbitals: the dxy, dyz, dxz, dx square minus y square, and the dx square orbital. That orbital is completely filled. Then comes the transition d block metals. The transition d block metals. The transition d block metals within the d block family, according to IUPAC, are those metals that possess incomplete or partially filled d orbital, as shown in the schematic in the next slide. And like we said earlier, there are d block metals, but because they have single electrons in the penultimate orbital, they are called a different name, and they are made up of scandium. For scandium here, in its ground state, he would present a D1, but chemistry has it that he can only form compounds in the +3 state, and in its +3 state, scandium does not contain any D. It does not contain any D electron in the fourth quantum state, which is the 3d orbital. That is the reason scandium is put here as being a non-transition metal. Copper forms stable compounds in +1 and +2. In its +1 state, if copper loses 1 electron in its +1 state, to satisfy the zero half completely filled phenomenon, the remaining 1 electron will readily jump into the D9 orbital. And if it jumps into the D9 orbital, copper shall lose its ability to be called a transition element, because its d orbital shall now become 10. But if copper goes ahead to lose the 2 s electrons, he shall therefore remain as a transition metal. Zinc in all forms, as we know, in its 30 ground state, is a non-transition metal, because in its ground state of 30, zinc will have a completely filled d orbital. Likewise, in its +2 oxidation state, it shall have lost the 4s electron, therefore still remaining with completely filled d orbital. So for that reason, zinc, copper, scandium are not transition metals. We shall review them later. At this point, I may allow you to justify why cadmium 48 and mercury 80 are not considered to be metals. But here we have the electronic configuration of the transition elements, and they have this single electron. There is no pairing in the xy minus y and the z squared. The x square minus y square and the x square do not have paired electrons. And because these electrons are not paired, every atom that presents this situation, you always expect it to be a transition metal. In the course of our study, we will review the properties, the magnetic and the spectral properties of elements that show this quality. At this point, I will leave you to review whatever you have learned, and please hit the subscribe button and we'll upload